Well, I'm going to do a little experiment on us here. I'm going to see how two talks about statistics after you eat dinner aids in digestion. Everybody loves statistics class, right? I mean, that's the one thing that you look back on your time in college about the grand times you had in statistics and memorizing all those formulas and stuff. I'm basically going to echo everything Greg just said. I'm going to say the same thing in just different words. I can't beat what Greg said, but I want to just give you some more examples along the same lines he did. So the first thing I want to tell you is about an experiment that this guy, Nate Bresnow, and a bunch of other people did. There was maybe 100 authors on this paper. And this is a fascinating experiment for us because it's an experiment about experiments. What they did was they handed out identical data to a large number of researchers, large number of groups of researchers, and they asked them to solve the same identical question, to investigate the same question. I'm going to read it to you because I can never remember it. The question was, would immigration reduce or increase public support for government provision of social policies? I think it's a little difficult to remember. It's hard to keep all this stuff in mind, and I want to give you some other examples. So I want to just classify this as, does X affect Y? Does X affect Y? X, immigration, affect Y, support for certain policies. Now that's causal language. Does X affect Y? And I think that science is about cause. The fundamental goal of science, of course, is to understand nature, to understand exactly what nature is. And that means understanding exactly what's going on. And that means understanding what the causes are. And if you truly know what the causes are, you can make those predictions that we're talking about. So that's what they did in this experiment. It was just exactly the right thing to do. Now they sent all this out, and I can't stress enough, this is identical data. Everybody had the exact same data, and they were asked the same exact question, but they were left free to investigate it however they wished, with any set of modeling tools that they wished. About a quarter of the models came back. I should say they were first able to answer this question. Does X affect Y, yes or no? And maybe we don't have enough data to tell. Only one group of researchers came back and said they could not tell. Everybody else provided a definite answer. One group, one quarter of the models that came back said, yes, X affects Y negatively. More X, less Y. More X, less Y. More immigration, less support for these public policies. And all of these results, this quarter of results, were significant. That's the word we're going to come back to, significant. And they were allowed to give an estimate of the effect size, the strength of the association between these two things. And all of them were significant, but some of them were very strongly significant, and some were just less so, but they were all still significant. Now, maybe you see this coming, but another quarter of the models answered completely oppositely. They said, yes, X affects Y, but positively. More X, more Y, more immigration, more support for these policies. Completely diametrically opposed. And just like the first group, all of the quarter in this group said, yes, it's significant. Our results are significant. So you have two groups, a large number of groups, and they're at war with each other. Every one of them providing a definite answer. That left about half the models. And those were split roughly in half too. Some of them said that X affects Y negatively, and some about X affects Y positively, but they weren't quite significant, but they were still sure of their answers. Now, this should sound wrong to you. If you're thinking, this absolutely must think, there's only one right answer. I don't know what the right answer is. And the answer might even be that there is no association whatsoever in the one group that did not want to turn in a model. They were the right ones. I don't know. But this is the interesting thing about this is that because there can be one only right answer, many people have gone wrong. A lot of science has gone wrong. But every model that was turned in was science. And as you heard from Greg, we have to follow the science, don't we? We're all told to trust the science, follow the science. But whose science? So that's what we're going to talk about a little bit tonight. Now, Well, these models, this was a sociological question. We already had a question about some of the weaknesses in sociology and other fields like psychology and education and so forth. And it's not really too surprising. These fields there's more controversy and so forth and perhaps more error. Because look, of the hideous complexity of the subject, people's behavior, and groups of people's behavior, that's really difficult to know what's going on with groups of people or even just one individual. So, you know, when we're talking about that kind of science, sometimes we call it the soft sciences. So to investigate the philosophy of science, most people don't think about these things, and they instead go to what they call the hard sciences, like physics and chemistry and so forth. And they think, well, now we got real science happening, and this kind of stuff that happens in sociology and psychology doesn't really happen in physics, or not that often. Well, it does. Physicist Sabine Hossenfelder, in a Guardian article, I think it was last year, she gave this quote about particle physics, about the state of particle physics, and I want to read it to you because it's important. She says, since the 1980s, I'm quoting her now, physicists have invented an entire particle zoo whose inhabitants carry names like preons, fermions, dion, magnetic monopoles, simps, wimps, wimpzillas, axions, flaxions, erebon, accelerons, cornucopions, giant magnons, maximons, macros, wisps, fits, braions, skyrmions, chameleons, custicons, planktons, sterile neutrinos, to name just a few. Now, the thing about, end quote, the thing about that is none of them turned out to be real. Not one. And there were many, many more. So it's not just psychology and sociology and the like, it's physics too. Now, she blames in part the idea of falsification, because as long as you're providing falsifiable propositions, why then you're doing science. But I think that's part of it. I think the real thing is just human psychology. Physicists want to be the people who are discovering that new particle, so they get to name it and everything. So there's great motivation to better themselves by coming up with these kinds of things. Still, there's a bright side to that, because, as I said, none of those particles turned out to be true. So what they did is the right thing. In the end, they invented all these things, perhaps too giddily, but in the end they checked. Can we predict and see this stuff again happening again? And the alters turned out to be statistical anomalies. Now, one thing I didn't emphasize in the Breslau thing was the number of models that were turned in. It was 1,200. I wanted to save that little tidbit. 1,200 models. Actually, it was a little bit more. 1,200 models. Now, with that being the case, we have to conclude, we're forced to conclude, and looking at what the physicists did too, doing science is easy. Creating models is easy. Positing theories is easy. It's real easy to do this. And so that's part of our problem right there. We've got so good at this that we're doing too much of it. And that's, and you think about what happens. I only gave you just one example, and Greg gave you a few, and Brett mentioned some at the very beginning. What if we apply all of this to all of science? What do we have? Well, we have that replication crisis we talked about. And it was just funny. I didn't talk to Brett about this beforehand, but he mentioned in the one set of study of medicine, they tried to, what they did is a lot of groups of people from economics and sociology and physics and all big name fields, they wanted to know how good the results were holding up. So they looked at the top papers written by the top people in the top journals. And they recreated the experiments. They redid them. They redid them, seeing how well they're going to hold up. Now, it doesn't matter which field you're at, which branch of science you're doing, the result, remarkably, was about the same. Only 1/4 of the results were the same direction and size as the original experiments. Didn't matter the field. A few more were about the same effect, but not the same strength of association, and the rest absolutely failed. Now, that's very interesting. So it's that same 1/4 we find everywhere. And that's kind of, if we think back to what we just talked about, Breslau's experiment. We got 1/4 of the models saying yes, and 1/4 positive, and 1/4 of the models saying negative. We got that 1/4 in here again. So that's interesting. I'll give you just a couple examples here. You can go on and on about this all day. They've done a lot of these replication studies right now. We've already talked about John Ioannidis. He looked in medicine, and he looked at the creme de la creme of papers in medicine, which is to say the most popular papers, the papers that got the most citations, 1,000 citations each or more. It had to be to make his list. He found 49 papers. Incidentally, scientists love talking about their H indexes, citation counts, impact factors, source normalized impacts per paper. They discuss these metrics in the journal metrics they publish again. I mean, they talk about these things more than Instagram people talk about their likes. I think scientists invented social media. You just listen to them talk, and this is the kind of thing they talk about. Anyway, Ioannidis found for the top 49 papers, the absolute top of the papers, 16% were about that replicated in the same direction as the original. The British Medical Journal in 2017, I'm not going to bore you with a lot of these results, but this one's interesting. They looked at new and improved cancer drugs. So in Europe, it's pretty much the same like here in the United States. New drugs have to be approved by the FDA, and you have to submit certain statistical evidence and that kind of a thing. Same thing in Europe. And so the drugs all met this test to be released into the wild. And so they looked at them several years down the road after being released, 39 drugs, cancer drugs. And after a while, only 35% of the new drugs had any important effect. About a third, about 2/3 had no effect whatsoever. And this is the kicker right here, I'll read you this. The magnitude of the benefit on overall survival ranged from about 1 to 6 months. That's it. From all this science, all this work, about an average of 3 months. It's not nothing, but it's not a lot. Now, Richard Horton of The Lancet, he was the editor of The Lancet in 2015. He's still the editor now. He said this, I want to read you this. The case against science is straightforward. Much of the scientific literature, perhaps half, may be simply untrue. Afflicted by studies with small sample sizes, tiny effects, invalid exploratory analyses, and flagrant conflicts of interest, together with an obsession for pursuing fashionable trends of dubious importance, science has taken a turn toward darkness. This is The Lancet. That's the top journal, perhaps New England Journal of Medicine. Maybe you can have a war there. Now that's the half of science that's wrong, or perhaps 3/4. This is the best science. This is still the top side. Imagine what it's like in the lower tiers where we don't have such, enthusiasm for the science. Now, you might have heard of this. There was a guy named Russell Funk and a bunch of others. They looked at the papers through the years. This appeared in Nature, 2-3 months ago. And they looked at what is called disruptive science. This is genuinely groundbreaking, fundamental new science, new fields of endeavor and things like this. They looked at that across every field, from physics to psychology, education, everything. It had plummeted since 1960. It's now down to almost nothing in every single field, in absolutely every single field. So it's impossible to look across the science that we're seeing out there and think that all of it, or even most of it, is any good or of any real use. There's a tremendous problem out there. And there's no symmetry here. Even if half of science is right and half of science is wrong, the half that's wrong takes much more energy and effort to combat and battle, especially because science is now run by the bureaucracy, largely. I mean, they control the mass amount of funds that goes on. And the people in charge are able to look at this sea of science, good and bad, and pick from it what they want. And they say, here we go, this is the result I want. This is now the science. And like Greg says, you ever know, they don't say this is science, they say the science. They say follow the science. That's why we need to lessen the amount of bad science that we have. So how do we do that? Well, other people have looked at this. In 1960, across the entire world, in all fields of science, there were published about 250,000 papers. That has now gone up to about 8 million papers a year, and it's just skyrocketing. It's still shooting north. So because of all the bad science we're seeing, because of this glut that we have, Well, what's the problem? The problem is there's too much science. There's too much of it. There's too much money involved. There's too much prestige involved. There's too many people doing science. There's too many people doing poor science, calling it good. And the solution to this is easy. It's really simple. Stop doing so much science. But that's not going to happen. You're not going to see any politician come up there and say, you know what, all right, you know what, I'm for less funding for science education, so we're not going to have so much of that. I'm going to cut back on the budgets to the NSF and NIH. It's not going to happen. So we have to live with this. We have to fix it some way or another. All right, so now I'm not going to go on about politics anymore. I want to know what counts as bad science, and let's think about that a little bit. And what produces it, besides just the glut of it, what else produces it? A lot of the reasons we already know about, and a lot of the stuff you guys know about, like peer review. It's true. Scientists, you've heard it all the time, scientists must publish or perish. That's an absolute fact. They must publish. So that accounts for this glut of papers. They have to put something out all the time. And this is Richard Smith now, editor of the British Medical Journal in 2015. He said, if peer review were a drug, it would never get on the market because we have lots of evidence of its adverse effects and don't have evidence of its benefit. It's time to slaughter the sacred cow. It won't be. It won't be. Peer review is too necessary to the journal system, which scientists need for their bona fides to make their money. So we can't change that system fundamentally. With peer review, it adds to the surfeit of papers that we have, and it guarantees a system. It guarantees banality. It penalizes departure from consensuses. It limits innovation, and it drains time. Almost as much time, I don't know, do we have a lot of working scientists here? Almost as much time as it takes to write grants. For not only must you publish, you have to provide overhead for your dean. And if you don't, you're not going to be able to keep your job at a lot of major research universities. So that's a problem. Also, finally, we come to the philosophy of science. That's ostensibly our job up here. And I wanted to start with that, but I couldn't. I didn't think I could because science is held in such awe, great awe, which a lot of it's justified, but a lot of it's not, as we've seen. And I had to at least kind of weaken that awe that a lot of us feel before I could tell why I think science goes bad in detail. So that's what I want to do right now. Now, again, I said at the beginning, I think science, the job of science, the fundamental job of science, the detail that Greg talked about, how to do it, you know, the mechanics of it, of course, I agree with that, absolutely. But the fundamental goal is to understand nature. And if we understand nature, we need to understand cause. Why and how and when X causes Y. And that depends on a philosophy of nature. You need to have a philosophy of nature. You need to have a philosophy of uncertainty and of what models and theories are and the like. Now, there's a lot of dispute in these areas and so forth. I'll just give you one. We can't do all of that, so I'll just give you one flavor. There's people out there who call themselves instrumentalists. They don't think cause is the most important thing. They're satisfied with statements like, if X, then Y. If X, then Y. That's different than X causes Y. It sounds similar, but it's not quite the same. It only says that if X happens, then Y will follow. It doesn't say why. Doesn't give you any real details why. And it's not like it's not useful. It's darn useful. You think about a lady getting on a plane. She has no idea how the engine, in conjunction with the wings and the fuselage, work to get the plane to fly. But she knows the plane does fly. If X, then Y. It's not completely useless or something. It's a first step. And scientists do that all the time, of course, by varying conditions in their experiments, just to see what's happening. So that's one part of a philosophy of science that's useful, but doesn't get to the core of things, which is cause. And so now what I want to do is lead us through 6 or 7 short examples, what I think are the main ways that science goes wrong by inattention to philosophy, and not paying attention or paying heed to these important philosophical differences. Now, I'm going to start with, I think, the easiest to explain and understand and to the most difficult. I'm not going to go through every possible way or anything like that, just the ones I think are the most productive of bad science. And we do know that there's lots of bad science. We've already seen that. The number one way is this. X, the X we've been talking about, is not measured. But a proxy for X is and everybody forgets the proxy. So X is not measured, a proxy is, and everybody forgets it. This one is extraordinarily popular in epidemiology. We've all heard from epidemiologists these past 3 years. Without this fallacy, the field would be largely barren. Let me give you an example. PM 2.5, you might have heard of it. It's dust of a certain size. It's all the rage right now, and everybody's investigating it for all its supposed deleterious effects. And you'll see lots of papers, PM 2.5 linked to or associated with heart disease or some such malady. And those are kind of sort of causal words, but not. They have technical definitions which allow them escape clauses when it turns out not to be true, if it does. And so they want to say cause, and they're very happy to have people infer cause from those words, but they don't actually mean cause. So the problem with all these studies, every study that I've seen anyway, is PM 2.5 intake is never measured. Never measured. But they'll still say PM 2.5 causes heart attacks or heart disease. Now, why? How does that go bad? I'll give you the example that the American Heart Association, we don't need to know the names of these papers, I have them if you want to talk to me afterwards, touts for their main study of the deleterious effects of PM 2.5. Here's what they did in this experiment. They took the zip codes of where people live, or rather their primary residences. This is going to be hard to follow. They got where they live, and they got the distance from a major highway from their home. Then they have a model of pollution produced at that highway. Then they have a land use model of how the PM 2.5 goes back to their primary residence, where it is assumed that the model's guess of the PM 2.5 at the residence was the exposure to PM 2.5, not the intake. Not the dose, the exposure. So we have, in the end, I don't know what's going on. It's not that PM 2.5 doesn't cause heart disease. It may not, I don't know. But the problem we have here is overcertainty, vast overcertainty. There's far too many steps in that causal chain to know what's going on. So that's, can I indulge you with, can you indulge me, but just my absolute favorite example of this? This is, I tell this one all the time, but it's my favorite one. The Kennedy School, Harvard's Kennedy School, some researchers claimed X causes Y, that attending a 4th of July parade turns kids into Republicans. Parade attendance was never measured. Instead, they measured rainfall at the location of the residence of where the kids lived when they were children. If it rained, they said, no 4th of July parade could have possibly taken place, and so the kid didn't go to one, even if they were away at their grandmother's or something like this. And if it was sunny, or it didn't rain, no precipitation, could have been cloudy, they said a parade happened and the kid went there with no measurement. And they used causal language. This made all the papers, it was on all the news a couple of years back. Experiencing 4th of July in childhood increases the likelihood that people identify with and vote for the Republican Party as adults. Well, I'm a meteorologist by training. It never rains in San Francisco in July. It should be a hotbed of republicanism. Right? Harvard. We'll get to why they came to that. Anyway, number 2, the second most popular way that things go bad by not heeding philosophy. Y is not measured, but a proxy for Y is, and everybody forgets the proxy. And sometimes neither X or Y is measured, and I call it the double epidemiologist fallacy. These are my fanciful names. You're not going to find them out in the literature or anything like this. The CDC is a big user of this fallacy, I'm afraid to say. That's how they talk themselves into mask mandates. In spite of a century's worth of studies, we have a century's worth of studies showing masks do not slow or stop the spread of respiratory viruses. Starting from after the Spanish flu pandemic in 1917, 2 years later, they started doing these studies. We got studies all the way up through. We have studies in operating rooms where in a major hospital in Britain, the surgeons weren't wearing masks for like 6 weeks. No difference between infection rates and everything. On and on. And in 2020, March 2020, there was a major meta-analysis that came out. Coincidentally, the paper was in the works for some time before the COVID panic hit, showing it was flu, not COVID, because no one knew of COVID at that time. Masks did nothing. Masks did nothing. But it was ignored. It was just ignored. So how did the CDC come to their belief that masks work? Well, they looked at cases. Up until 2020, cases meant people who were seriously ill and sought or needed treatment, and we differentiated them from infections, but that all changed in the panic. Anyway, they looked at cases in counties with and without mandates, or rather, they looked at rates of change of case rates from county to county with and without mandates. And they said, look at this statistical model we have here. That proves that mandates are good, mask mandates are good. Doesn't work that way. Neither X nor Y has been measured. Nobody was measured wearing a mask or not, and nobody's infection was measured or not. But they did do one study like this. Maybe you've heard about it. It was in Denmark. Early on in the panic, they did in Denmark, they handed out N95 masks to thousands of people and trained them in their use. They got free masks and trained in the use. And another group went mask-free. Thousands of people. And at the end, they measured individuals. Did you get an infection? Did you get an infection? Did you get an infection? They measured this. That's the exact way to do the experiment. No difference in the groups. And that study was excoriated because it was not a pleasing result. All right, number 3, attempting to quantify the unquantifiable. Number 3. Now, one of my favorite novels of all time is Little Big Man. Don't watch the movie. It's terrible. It preaches the exact opposite message of the book. But it tells the story of Jack Crabb. Maybe you've heard of the story. He was a white boy in 1850 in Wyoming, what's now Wyoming. And he was adopted into a Cheyenne clan and raised among the Cheyenne. And many years later, he ended up back among the whites. And he is amazed at all the quantification he sees. He said, that's the kind of thing you find out when you get back to civilization. What date it is, what time of day, how many miles from Fort Leavenworth, and how much the Sutlers is getting for tobacco there, and how many beers Flanagan drunk, and how many times Hoffman did it with the harlot. Numbers, numbers. I've forgotten how important they was. And I think sometimes too important. I say this as a mathematician, statistician. Let me ask everybody right now, this is important. We're gonna do an experiment here. How happy are you, it's a statistics talk, so it's gonna be high. How happy are you on a scale of negative 17.5 to e, the natural number e cubed? Well, all right, we could be serious and treat it. I'm gonna do it, I'll say 1 to 5. Now that makes it science. Now I can call it a Likert scale because I'm quantifying it with integers instead. And I'm not going to call it the happy score. I'm going to call it the Briggs instrument. They call these questionnaires instruments, and they attempt to borrow with that name the precision and rigor of things like the Werner calipers and oscilloscopes and the like. So now, suppose I pulled, which hat looks more bored? That's kind of hard. It's statistics. So let's see this hat. These guys are smiling more than you over here. So let's suppose I asked this room over here. I asked everybody the happiness, the patented. They're all copyrighted, these things. The patented Briggs score over here, and I asked over here. And I found out that there was a difference in these scores. And then I say that the people seated to the speaker's left are going to be happier than people seated to at the right for after-dinner speeches. Well, that's how the science of this kind of thing is done. That's exactly how it's done. It's precisely how it's done. And anyway, what does happy mean? This is one of the things I want to read you. The thesaurus. I'll just read you a couple of these. This is important. Accepting, accidental, ad rem, adapted, addled, advantageous, advisable, applicable, apposite, appropriate, apropos, apt, at ease, auspicious, beaming, beatific, beatified, becoming, beery. That's my favorite. Befitting, bemused, beneficial, benign, benignant, besotted, blessed, besotted's pretty good too, blind, drunk, and so on. On and on. Each of these is a genuine shade of happy. All right, each of these is a genuine shade of happy. And it's not like I give this instrument out. If I got a person who answered the absolute top and a person who answered the absolute bottom, I'm not saying that this doesn't say there's some difference in happiness between these people. There might be, there probably is, but I don't know what that difference is. I don't know what shade of happy these people have in mind. And so how do I tell? Well, the typical answer is to say, well, the instrument has been validated. What does that mean? It doesn't mean that I'd send the oscilloscope out to some master thing and I'd calibrate it next to it. No, it just means I give the questionnaire out to another group of people and the answers come back about the same. That's not true validation, which can't be had. But we fool ourselves into doing it. And why? Because that's the only way we can use these statistical methods. Psychology is one of the biggest abusers, as we learned. Because without these quantifications, there's no statistics to do on them. So we can't quantify the unquantifiable. All right, here's one of the big ones. Mistaking correlation for causation. Now, every scientist knows that you must not logically imply causation from correlation. Everybody's heard that, right? Correlation does not imply causation logically. Just like confirmation bias, though. Everybody's heard of confirmation bias. That's for the other guy. Now, you could tell in Bresnow's group, I don't know, they didn't do a poll of these people afterwards, but I bet you the people in the opposite camps each believed that they had the right answer and the other people didn't. There must have been a lot of confirmation bias going on in there, but nobody's going to admit to it. Nobody who's producing bad science is going to say, I'm the guy. It just doesn't happen. That's not how people work. So, why do people mistake correlation for causation? Well, the practice of announcing measure of model fit to data. The practice of measuring model fit to data. The Lancet's Horton, we met Horton earlier. He said, our love of significance pollutes the literature with many a statistical fairy tale. This is a big problem. Everybody knows about the problem, but nobody can wean themselves off of this. What does significance mean? Nothing to do with the English word, significance. It means having a wee p-value. That's all it means. And having a wee p-value means it's significant. There's so many things wrong with p-values. I mean, we could spend an hour talking about them or more. Should we? No. All right. I'll just leave it at this. When a wee p-value is found, it means this. It means that there's correlation in the data. That's what it means. But we can't infer causation from correlation. But that's what's done. That's exactly what's done. Everybody infers causation from this correlation, knowing they're not supposed to do it, but they do it anyway. They can't stop themselves. Gerd Gigerenzer, who Greg mentioned, he calls it a ritual. It's science as ritual. It's exactly that. We come up here, we bless the data, we get the wee p-value out. If you can't get a wee p-value out of your data, you're just not trying hard enough, as Bresnow's experiment proved. So we just have to abandon these things. But I'm not going to give you a lot of examples on that. I'll just say that it accounts for all those headlines you see. I gave this example out in Phoenix. You see these medical headlines all the time. The headlines I like, these are actual headlines from writing about actual medical trials and the like. 1 egg a day lowers your risk of type 2 diabetes. That's causal language. You eat an egg a day, you're going to lower your risk of diabetes. Another headline came out just a couple of months afterwards. Eating 1 egg a day increases your risk of diabetes by 60%, study warns. These things, we laugh, but they're all over the place. And Ioannidis himself, he wrote a paper in 2015, I think it was. He just grabbed a cookbook, he thought it'd be fun, and grabbed just 50 random ingredients, and then went to PubMed to see how many of them are associated with or linked to cancer. Just about every one of them. Everything is, it's too easy to find a correlation. And the causality of cancer is not just simply you're going to eat an egg or anything like this and you're going to develop cancer. It doesn't work that way. So model fit is, of course, it's nice. We need it. It's a necessary criterion of that your theory is working as it should, but it's not enough. We can't do it. You need to have much more than this. You need to have predictive success. So we need to have that predictive success. And you'd be surprised. The physicists at least did that predictive check of their models. They're very enthusiastic about building models and making them, but they at least went back and checked. They made predictions with these things, found out they were poor models, and they abandoned them. But that never happens in the other sciences. People write a paper, out in the world they go, and they're satisfied they're done. They never check it. That's why we have the replication crisis. That's why so many of these papers fail, only a quarter of them coming back in the same shape they left. That's how science improves. But physics is improved, if it's improved at all, just because they've done these kind of predictive checks. This is what Greg's dad said, Jeffrey Glassman, in a book. He wrote a book on an excellent book on how to do science that a lot of educators should read and so forth. Evolution in Science. He says theories grow by eating their young. They feast on their own predictions. And I thought that was perfect. I think that's where Greg grew up learning this kind of stuff. But only the good predictions. They choke and die on the bad ones, as they should. But we don't have that. We don't have that in most fields. It's just not existent. I promise you, it's not there. All right, number 5. We're getting more in depth, and it's more complicated as we go along these things, as I promised you. So I wouldn't blame you for not following all of this. It's the multiplication of uncertainties, or rather, the forgetting of multiplication of uncertainties. Now, you all look like nice people. Most of you haven't walked out or fallen asleep, which is what I predicted. So there's my model, it failed. And so I'm sure you all want to save the planet. Yes? We don't want the planet not to be saved from global cooling. Well, when climatology was not quite an independent field, there weren't a lot of people doing climatology back in the 70s. People really did say a new ice age was coming. This happened in Newsweek, 1975. I'll read you this. There are ominous signs that the Earth's weather patterns have begun to change dramatically, and that these changes may portend a drastic decline in food production. 1974 Time. Climatologist Kenneth Hare, a former president of the Royal Meteorological Society, believes that the continuing drought gave the world a grim premonition of what might happen. Warns Hare, I don't believe the world's present population is sustainable. We've doubled since then. Now, there's scores and scores of these, and scientists and groups like the UN warning of mass deaths and starvation and so forth, which did not happen, and then we got global warming because the weather changed, it got warm. And after a while, the weather failed to continue to warm, and we got climate change. Climate change. Now, that's a brilliant name because the Earth's climate never ceases changing, not for an instant. It has never stopped changing. We'll always have climate change. And so you have this weird circular argument that the changes we're seeing are because of climate change. That's what the climate does, it changes. We can't have changes because of climate change. So you get this. But that's okay, we can live with that kind of circularity. But that was quickly married to scientism. We'll discuss scientism in a minute. When doubts about climate change became synonymous with doubting solutions to climate change. Solutions to climate change. And because of this error, the doubt you expressed in the solutions to climate change, you're called a climate change denier. Now that's an asinine name because no working scientist at all, none, not one, denies that the climate changes or is unaffected by man. So we have things like this. Janet Yellen, I think it was just the week before last, at a congressional hearing, she said, climate change, inflation is transitory, Janet Yellen, that one. Janet Yellen recently said, climate change is an existential threat, and the world will become uninhabitable if, can you see it coming? If we don't act now. Uninhabitable. Uninhabitable. That's a mighty word. That's a mighty word. So these two guys were curious about this in 2021, and they looked at these apocalyptic predictions. That's their word, apocalyptic predictions. And they really began around the year 1900 or so, if you can believe it. But they didn't pick up steam until the 70s. And the average age of the time we have left until the end comes, there's some variation, but the average age is 9 years. So starting with people like Paul Ehrlich in the 70s, we have 9 years left, and we have a lot of 9 years left. We currently still have about 9 years left. The funny thing about this, this is what I want to say, because we're up here preaching the predictive method in science, which is necessary, but it's not going to save science from everything, because these failures and these apocalyptic predictions have not dented the theory or the belief in the theory at all. So it's just prediction alone. It's not going to save us from these kinds of a thing. All right, so I owe it to you to talk a little bit about the science of climate change. We could talk about the thermodynamics of fluid flow on a rotating sphere and all this kind of stuff, but that's too much for us. So I want to talk about the things that are said to go bad because of climate change. What's going to go bad because of climate change? Everybody know? Everything. Absolutely everything. If it's absolutely, there's a guy in England. He collects what's called a warm list. The site is called Numbers Watch. He stopped collecting these a few years back. I guess he's elderly, I think. And he was up to like 900 papers, and he looked at academic papers. Here's what's going to happen because of climate change. Here's what's going to happen. I'm just going to read you a couple of them. These are the things that are going to go bad or get worse. AIDS, Afghan poppies destroyed, African Holocaust, age of deaths, poppies more potent, Africa devastated, African conflict, African aid threatened, aggressive weeds, Air France crash, air pockets, air pressure changes, airport farewells, virtual. They nailed that one. Airport malaria, Alaskan towns slowly destroyed, Al-Qaeda and Taliban being helped, allergy increase, allergy season longer, my favorite, alligators in the Thames. We haven't even come close to getting out of the A's. Look, anything that is supposed to be good or benign or delicious or photogenic, climate change is going to kill right off. And if it's bad, if it's a weed, if it's harmful, if it's a poisonous spider or a snake, climate change is going to cause to flourish. Now, there's not one study that I know of that a slight increase in global average temperature is going to increase pleasant summer afternoons. Nothing like this. It's only bad things. That a small change in temperature can only be bad. And totally and entirely bad. It's sufficient proof, I think, that science has gone horribly wrong. It's not logically impossible, but it can't be believed that changes can only be bad. Now, that doesn't say how the beliefs are generated, and I'm not going to go into too much detail about this, but the way it works is this. We first have a model of climate change, all right? And that's not certain. We don't know what the predictions are going to be exact. They're not absolutely certain. And on top of that is usually some kind of weather model. We need a weather model because the alligators in the Thames are affected by the weather, so we need a weather model on top of that. You guys know how accurate weather models are. Then we need a model of the thing itself, like poppy production and African aid and all that kind of stuff. That model is even more uncertain. And finally, we have a solutions model, where we say if we do these solutions, we're going to be able to fix all this kind of stuff. Now, really what you have to do is multiply these uncertainties. It's like multiplying a head after a head after a head after a head of a coin flip. It's a half the first time, but by the time you get down to 4, it's 1/32. You're just going smaller and smaller and smaller. So it's the bandwagon effect. It's people jumping on these things because everybody else is doing it. It's just, if you're basing it on p-values and the like, it's just far too easy to do. And they're all surmises. They're all guesses of what things are going to be like. And they're taken as gospel, all of these kinds of things. It doesn't make any sense. That's it. That's the multiplying uncertainties. Scientism. Scientism, I'm only going to talk about a very little bit. Greg mentioned a little bit about it. Scientism is the belief, the false belief, I think, that science has all the answers. Not just some, but all the answers. That science knows right from wrong, good from bad, moral from immoral. That science knows what to do. Well, that's false. Science can give you predictions and give you the uncertainty around those predictions, but that doesn't tell you what's right or wrong to do. And so that idea that when people say, we need to, this is my program, my solution, we need to follow the science. When they say, we need to follow the science, they mean, we need to follow me. Because that's what it really comes down to. That's not what science says. Science is absolutely mute on right from wrong. And there's two kinds of science, scientism. I'm only going to bother you with one, just a real quick one. I call it scientism of the first kind. Scientism of the first kind is when when knowledge that's been obvious or known from the farthest reaches of history is announced finally as proved by science. It's kind of a gateway drug to the deeper kind of a scientism, because we don't need science to tell us what we already know. But if we're looking to science to tell us before we really commit ourselves, we're in a kind of a world of hurt. And I'll give you one example. The Army hired a certain corporation, the United States Army, hired a certain corporation to investigate whether there were sex differences in physical capabilities. Guess what they found? That's scientism of the first kind. Yeah, some of it's political cover and all that kind of stuff. I understand, but that's what it comes. Okay, finally, the last, you'll be happy to hear, the last and most difficult, what I call the eighth deadly sin, the deadly sin of reification, mistaking models for reality. When we come to believe our models are reality, we are committing a very bad sin. It's very difficult to explain this. We're in rugged territory because we're getting closer to the true nature of causation, which requires a clear understanding of metaphysics, and therefore the subtler mistakes we could make in explaining it and understanding it and so forth. And the more difficult it is to describe, plus I've kind of taken up enough of your time. So I'm going to give you one instance of the deadly sin in two flavors, both very current. Now, I want you to just think of this. I want you to agree with me on something here. If we can agree with this, we can go forward. I think it's an obvious fallacy to say that Y, we're back to our X and our Y here, to say that Y cannot or has not been observed when Y has indeed been observed because a certain X, some theory says that Y cannot be observed. Does that make sense to you? Did I explain it well? We actually see a Y. We observe this Y happening. But a certain theory, a beloved, well-beloved theory says we can't see the Y. Therefore, what we've seen is not true. I think that's a fallacy. That's the fallacy of the deadly sin of reification, because this happens in all the time, as a matter of fact. And it's usually when X is some cherished theory. When Y is an observation that's scoffed at or dismissed or explained away because it does not accord with the theory. The theory becomes more important than the observation. Now, this happens in the least sciences. We discussed some of these earlier, like dowsing and astrology, where its practitioners routinely explain away their errors. They don't accept their failed predictions. They say, no, the causes weren't right, the moon was in the wrong phase, all this kind of stuff. They give all kind of reasons. But it also happens with great and persistent frequency in the greatest of science, like physics. Now, the most infamous example of our Y is free will. There's lots of subtleties in the definition of free will, and we can go on and on about that. But for us, any common usage or definition will do. Well, we all observe we have free will. Choices confront us, we make them. There's our free will, there's our Y. But they say, some people say, because of a certain X, the theory of determinism, which says all there is are just blind particles or whatever they are, bumping into each other, following something mysteriously called laws, explains everything. So everything is predetermined by these things, so free will doesn't exist. So determinism really does prove that free will does not exist. But free will does exist because we have it. So there must be something wrong with the theory, but they will not give up on the theory because the theory is too beneficial for them. Now, I promise you, you're going to see this. This is a little homework exercise for you. Go and look at any article out there. You'll find that some computer scientist or physicist or anybody explaining that free will does not exist. And in every one of these articles, you're going to find a variant of this sentence, which I think is profound and hilarious. I promise you, you'll see this. They all say something like this. They first say that you don't have free will, and it's obvious you don't have free will. Of course we don't have free will. And if only we can convince people that they cannot make choices, they will make better choices. Look it up. Don't trust me. Look it up. Now, this deadly sin of reification also leads to the current mini-panic over artificial intelligence, AI, you've heard this, which is no kind of intelligence at all. All models of any kind only say what they're told to say, and AI is just a model. AI is nothing more than an abacus. Everybody knows what an abacus is, which does calculations in wooden beads at the direction of a superior, real, genuine intelligence, but AI does the same thing in a computer with electric potential differences. That's it. There's no intelligence there. It's just a model doing what it's told to do. There's no reason to panic over AI. We should panic about the intelligences behind artificial intelligence. That's true. That's absolutely true, who direct these things and use them in all kinds of ways. That's all true. But the allure and the love of theory is just too strong. They believe that somehow intelligence is going to emerge just as it would have. I guess if you threw a pile of abacuses over the floor over there, and it's going to come alive and become intelligent and take over the world. It just doesn't work that way. And you hear about emergence everywhere from quantum mechanics on up. I always say it's a great grand bluff. They have no proof of it. It's raw assertion. It's a power play. They'll look at you, but we know it's going to happen. It hasn't happened. They don't know how to explain it. There is no theory there, but they'll try to bluff and bully you into believing it. You'll get this every time for these people. All right, there are alternatives to this philosophy. We have no time to talk about this, like Aristotelianism, a return to that, which would do wonders for quantum mechanics if it were better known. And the deadly sin of reification is much worse than I've made it sound, much, much worse than I've made it sound. It leads to strange and untestable creations like many worlds and the multiverse and things like this in physics, and gender theory, the love of model and the love of equality and all these kinds of theories. Well, that's all I have to say about bad science. Maybe I'm wrong. So I'll leave you with the most quoted words in all of science. More research is needed. Thank you. Can I have this, Brett? Can I have this?
We could do a brief Q&A.
I've spilled it everywhere.
So, Professor Briggs,
yes, sir.
In the spirit of scientific inquiry, I may offer 2 points, which may be opposite of what you were saying.
Sure.
First of all, that question about immigration, it is such a loaded and inaccurate question.
Sure.
Because when I am asked that question, I'm thinking, are we talking about legal or illegal immigration?
Yep.
And whether I'm thinking about legal or illegal, I may have different answers. So that's number one.
Okay.
Number two, you stated that masks were proved to be useless, but I would beg to differ in this respect. There were studies that were saying that the reason for infections is that people in the grocery store walk into somebody's sneeze cloud. And that's how you get infected. It stays in the air for a certain amount of time. Perhaps masks in that situation prevented those clouds from forming. And I would say it would be a good thing that I can,
Thank you.
that I can think of.
Thank you. All right, so for the first one about immigration, excellent point. They did, in fact, specify it more clearly than I'm leading on here. I'm not giving you the whole paper. But that's exactly right. That's part, when you're investigating something like that, those ambiguities always exist in the questions that the investigators are doing. Absolutely. That's part of the problem. We're not defining terms. They're not rigorous and rigid enough. And I will say that it's been known forever that, someone sneezing on you with a cold, you're going to catch a cold, unless you've already had it and been immune. But the problem with the masks is it's plausible. That's the thing. It's plausible. My God, it must be blocking something. I can't breathe so well through this thing, so it must be blocking something. But the virons, the particles themselves are so small, they just breeze right through it. And they've done, there's just dozens. There was a recent Cochrane review that came out just maybe a month ago or something like this, looking at dozens and dozens of these studies and over the years, over the last 50, 60 years. They just don't work. I mean, it would be nice to believe that they did, but they don't work. And in fact, what they do is, apart from some of the obvious things like perhaps you're breathing bad air and all that kind of stuff, I don't know how important that kind of stuff is, but they do one terrible thing. They spread fear. They spread terrible fear. Here I am walking down the streets of New York City. My wife and I were walking down the streets, New York City. And I'm without a mask. And here's a guy who sees us coming. He runs off into the street of Manhattan Street to get away from us because I must have the disease because I don't have a mask. And therefore, he's going to catch it and die, so he runs into Manhattan traffic. What's deadlier? No, I don't think masks should be encouraged.
Yeah, so you said something that seemed to imply that it was sort of buffoonish to look for new particles in physics.
No, I don't.
So standard model of particle physics, proposed mid-20th century, led to 30 fundamental particles, all the way up to the Higgs boson a decade ago. And it was immensely successful. People proposed a lot of particles. So it seems to me that's the next smart step, to propose new particles. Of course, some of them, will be discovered. Others won't. That's how science works. You toss out different hypotheses. You see which ones will work.
No question.
So, and I have colleagues here at Hillsdale and other places who propose these sort of particles. So why is that not a good idea given the very high success of the standard model?
The standard model has been in place since 1975 or so, and the Higgs boson's relatively new, just a couple of years old, the confirmation of it. So all of these new particles these are just the past few years. They're coming up with new particle, they notice these statistical anomalies and they rush to describe them with new particle creations and new physics. They want to be the first to explain all this kind of stuff. There's nothing inherently wrong with doing that per se, but there's just lists and lists and lists of them, and none of them are right. And why not instead look at what's going on with the? We don't have time to discuss quantum mechanics and so forth, but that's where this discussion would lead. Why not look at a different metaphysics of quantum mechanics, which is out there and available, and which leads a different direction than these kinds of things. And it's a tremendous problem because there's just for resources alone, all of these particles that are positive and in search for and rushed into print, it just leads to a lot of effort because then they have to go back and check and all that kind of a thing. It's a tremendous amount of work and resources. And you think that's what science is supposed to be for? Okay, but the success rate's very low, incredibly low. Maybe that's good, maybe that's bad. Should we be paying for it? Should all of us be paying for it? I don't know. That's the kind of questions we lead into. I'm not saying it's wrong. I'm saying physicists did the best job because they went back and at least checked. Well,
I think there's a couple of people that want to follow up on that, but my topic is a little bit different, and that is to do with the carbon dioxide in the atmosphere.
Sure.
It's going up by 5 parts per million or so every year, and yet it's never used as a measure of success. It's the one thing that can be measured pretty accurately, both in the northern and the southern hemisphere.
Sure.
But yet nobody ever talks about how we're going to either slow down that increase or stop it or reverse it. They always say it's associated with a temperature that we're going to change, which is almost impossible to measure globally.
Quite right. So I'll handle the second part of the question right. The global average temperature you hear about is a model. It's based on a very complex model with gross uncertainties in it. And what they should be saying at the end, the temperature is X plus or minus a predictive interval. And it gets into the real weeds here when instead they talk about a parametric interval, meaning they just talk about the model itself as if the model were true, and the vast overcertainty results. About slowing carbon dioxide down, well, that's only if carbon dioxide's a bad thing. Is it? I mean, plants thrive. It's plant food. I mean, the EPA classed it or tried to class it as a pollutant, but without it, all plants die and then we die. You can't have plants without carbon dioxide. That's what they eat, that and water. So it's not necessarily, it's not a given that we should indeed try to reduce carbon dioxide. It's just not a given because, and this is well known, I don't want to get too much into the physics of all this kind of a thing, but the effect carbon dioxide has on the lower atmosphere is logarithmic, meaning it tops out pretty quickly. The effect is you build up enough CO2 and then you get some warming for that, but then you don't get much or any after that. And so the only way we can have more warming is to build in certain feedbacks. We need to build in certain feedbacks about clouds and stuff like this, which are now just grossly parameterized in models that we don't know a lot about. And I'll tell you about the predictive success about climate models. It's not that good. Probably. Because an independent test of climate models has never been made. You can't have the same person who does your books do the audit, right? That doesn't happen. So we need to have these models independently checked. I don't have to be on this committee, but other people who have nothing to gain, no interest in what the results are going to be need to check that thing. I think such a thing is impossible because of the political climate. It would be almost impossible for a committee doing that to come to any conclusion but the foreordained one, I think. So we've seen prediction or after prediction fail. There's going to be more hurricanes? No, we have fewer. They're going to be more intense? No, they're not. They're lower, fewer. So they keep changing the metric. Instead of looking at just strength of hurricanes, we're going to look at wind speed cubed. There's good reasons to do that. And we're going to look at it only at certain times in the storms. So they keep trying to finagle and look at things that are going to confirm their belief. Nobody in these fields answers the one important question all scientists should answer. What would convince me? What evidence would convince me that I was wrong? You ask that to people and they say, oh, nothing, it's impossible. Or they refuse to answer. You know you're not dealing with good science there. Something has gone wrong. And that's a very common thing in many fields.
Yeah,
I keep looking at this like I'm speaking into it. That's a bad model.
Dr. Briggs, thank you so much for your speech tonight. I want to ask about the fundamental presuppositions that guide modern science. One of them is the idea that the universe itself is explicable, and that if we simply fund enough research, we'll eventually have a working model of nature in itself. But that seems to be fundamentally questionable. And it seems that science must be fundamentally rooted in skepticism, but you have a constant human inclination toward consensus and toward a desire for honor and money and fame, and that fundamentally seems to be the problem with modern science. And I want to go back to the question I asked Mr. Glassman about the nature of authority versus the desire to know. That seems to be, there's a problem there that seems to need to be explored, and I was just wondering if you could comment on that.
Absolutely. All of those things we all know the answer to that question. I think it's the obvious answer. But how do we get ourselves out of that? How do we escape from that kind of a thing? The problem is like I said, there's too much money in science. There's too much science going on. The consensus just builds and builds itself because it keeps growing. The number of scientists keep growing and so forth. So it looks like the people are becoming surer and surer when no new evidence is being given. So the only thing is to try to be independent from that. That's the only thing we can do, and to demonstrate that our models are better predictive success than the other guys' models. That's all we can. As far as the fundamental nature of and the philosophy of science goes and so forth, that's very difficult, and we need to talk about that in depth. Not here. We don't have the place for it here, but there's the idea that, I don't mean in the sense that Greg meant laws, but there's another view of laws that people use as if these laws are true and these are the governing things in the world. Well, there's another way to think about this. It's not the laws of nature, but it's the laws of natures. We don't have laws of nature. We have natures of things and things behaving, substances behaving in ways they have powers, causal powers and things like this. And typically physicists call those phenomenological laws and so forth. And they don't believe those are the fundamental ones, but I think they are the fundamental ones. This is a whole group of philosophers led by Nancy Cartwright and others and things like this. They call them the guys who think that the laws of the laws of the universe are the things that are guiding everything. They call themselves the realists, which is a great name. But the other people in our camp, we have to call ourselves anti-realists. So that getting there first. Computer scientists have learned that lesson. They're the best marketers in the world. Oh boy, deep learning, neural nets, machine learning, all this kind of stuff like artificial intelligence, all completely wrong, but lovely names. Well, thank you very much, everybody.